Hello there, children. Today, we are going to work on section 2.2, polynomial functions. This education experience is brought to you by your Peacekeeper Polynomials. That'll be me, Mr. Faust. So we're going to look at polynomial functions and how we can apply them. So what we have here is the leading coefficient test. Now, leading coefficient test can be found on page 98 in your books. However, we have two cases that deal with our biggest exponents. Now, all this really is, folks, is talking about end behavior. We do end behavior again, just as a quick review, telling us where the function's going to be going, so we can find out where it crosses our x-axis and makes zeros. So, just as a reminder, when n is an odd exponent, like an x to the 5th, x to the 7th, x to the 3rd, we have the following situations. Now, notice over here, a is greater than 0. The leading coefficient is greater than 0, like x to the 3rd. So as x goes to infinity, y goes to infinity. And as x goes to negative infinity, y goes to negative infinity. Meaning you put a positive number in, get a positive back. Put a negative in, get a negative back right there. And over here, a is less than 0, like having a negative out in front. You do the opposite. You put a positive in, get a negative back. You put a negative in, get a positive back. We've talked about this before at length. It's nothing really that new, but it's something we need to review a little bit for this section. Now, when n is even, we have the following situations. We have a being positive again, and a being negative. So an example of an even exponent, like x to the 4th, x to the 6th, x squared. So if it's even, whatever you put in the positive, take it to an even power, you get a positive. You put in a negative, take it to an even power, you get a positive back. Because a negative to the 4th power, or at any even power, is going to give you back a positive. Conversely, over here, as x goes to infinity and negative infinity, you take that to any even power, you'll get back a positive number. However, a positive times that negative out in front yields me a negative. And remember, in case we seemingly forget, which you're going to have to start remembering if you don't, it's okay for right now, f of x is the same thing as saying y. Should be a bit of a review for all of us. Now, to the meat and potatoes, burritos and rice, tofu and green beans, if you're the vegetarian variety here. We've got the following. Real zeros of polynomial functions. What the heck is this? If f is a polynomial function and a is a quote-unquote real zero, the following statements are equal. It means we have four statements. Statement number 1. X equals a is a zero of the function f. So that means if I'm telling you a is a real zero, that means if I put x equaling a, that's going to be a zero of my polynomial. Nothing earth-shattering with that one. If I'm telling you a is a zero, that means it's a zero. Okay, whoop-de-doo. X of a is a solution to the equation f of x equals 0. That means if you put this a value into my function, you're going to get back a 0. That's what it's saying. Hence why it's called a real zero. Nothing earth-shattering there. Now here's a different one. X minus a is a factor of the polynomial of f of x. That means if I'm telling you x equals negative 2 is a 0, that means x plus 2, or the opposite of that 2, is a factor. That's going to be a really important one for us. And finally, a comma 0, a0, is an x-intercept of the graph of f. So if I were to graph this function f of x, and I just graph it in, I don't know, blue, something like that, I'm telling you that negative 2 is a 0. That means that value right there is negative 2 comma 0. All of these, folks, are synonymous with one another. They are interchangeable. That means if you have one, you've got the other 3. That's going to be really important. So if I'm telling you it's a 0, I know the opposite of that becomes a factor, and I know that that's the intercept. If I know the intercept is a, x minus that a value is a factor, and that a value becomes a 0 and a solution to this part of the problem. That is huge for us. Speaking of zeros, so a very basic example here of what we do is find the zeros of this polynomial here. Now, we have some of our properties, and our property states that, hey, you know what I can do? If I set this thing equal to 0, then these things will be solutions. So that's what I'm going to do. And remember, by our zero product property from Algebra 2, if I set these fully factored forms equal to 0, I can solve them. Now, this is a very, very, very easy problem in terms of what we're going to do in this chapter. We square root here. We get x plus 7 equals 0. And then we solve, we get x equal to negative 7. X equal to 3. And x equal to negative 2. Those are my zeros of my polynomial. Now I do want to highlight something. I do want to highlight over here this 2. That's going to become very important for us this chapter. How important? How important, you might ask again? Repeated zeros of a polynomial. So, what that means, if I have something fully factored out, and it ends up giving me an x minus c to some number other than 1, we say that that 0, when I set this equal to 0, you would add c to both sides, x equals c, has multiplicity of m. So, for example here, x minus 3 to the third would be x equals 3, subtract 1 there, multiplicity or multi 3. Now, what does that mean for us? Well, it's going to affect us graphing later on. So, if my 0 has an odd multiplicity, like this one did, then my graph of f crosses the x-axis. That means it crosses the x-axis as such. No big deal, right? However, if a 0 series has an even multiplicity, then the graph of f is tangent to the x-axis, and the value does not change sign. Well, what does that look like? Well, it looks like this. Let me just erase this here for a second. Let's say I had x minus 2 squared. My 0 would obviously be 2, multiplicity of 2. When I were to graph this thing, my graph would go like that. That's what it means to lie tangent. Now, the graph could do other stuff around here. I'm just being very simple. But it would touch. It taps and moves on. So it's like tag and runs away the other direction. The value of x does not change sign. That means I still have a positive y, tag, still a positive y. That's what it means by multiplicity, which will become important when we're finding zeros later on. Alright, so let's find the real zeros of this following polynomial function I have for you here. We'll go x minus 2 to the third, 2x plus 1, and x minus 3. So, find the real zeros here. You're going to, well, it's already factored for us, which is awesome. We set each factor equal to 0. Now, recall, each factor gets set equal to 0 because I have the zero product property, which, if you forget what that is, a little bit of a refresher. It means if I have a bunch of things that are multiplied together, and I say they equal 0, one of these three has to, in fact, be 0. Alright, look at that, negative 1/2. And now here, so we circle, cube root here, and then we solve, and then we just state its multiplicity. Now, why do I have to state its multiplicity? Because later on, when I build polynomials from zeros later on this chapter, that's going to become an important thing to know. So don't just throw it out. Now, let's look at this polynomial right here. So, I can set it equal to 0 again, but I've got a bit of an issue right here. It's not quite as easy as the last one. I mean, that's not too bad, obviously. This one I have to factor. Two numbers that multiply to 16, add to a -8. That's -4 and -4 and -4 squared. And then we set each factor equal to 0. Don't forget the multiplicity here, folks. That's going to become really important. And then that becomes 2. Not earth-shattering. Not earth-shattering at all. But what if I have the following? But what if we get a problem like this? Okay, clearly not factored all the way yet, so let's take a peek. I want to use my factoring skills. Now, notice how all of these over here have an x in common. I'm going to pull that x out. Alrighty, so I pull that x out. Okie dokie. It's still here. Still not quite what I need yet. Factor this thing, two numbers that multiply to 32. But they are going to add to 12. That would be 8 and 4. And then we go ahead and set each of these factors equal to 0. Nothing earth-shattering there, nothing crazy. X plus 9 equals 0, that means x equals -9. No multiplicity needed. Here, x plus 4 equals 0. No multiplicity needed. Here, x plus 8 equals 0. So x equals -8, no multiplicity. And then, everyone always forgets about you, x. You're all by yourself. And it's up to saying, don't you forget about me. Set me equal to 0. Don't you forget about me. Set me equal to 0. Now, because usually if it's a coefficient, but it's not an x, no one really cares about it in terms of solving. But because it has a variable, I've got to worry about it. And everyone always forgets about that one. So you've got 4 zeros here. No multiplicity, but 4 zeros. So, now you are ready to tackle the next assignment, which you already ready on. So, oh happy days, you're here again. Proceed and enjoy.